Hello everybody, welcome to my video on risk and risk aversion. We're going to be looking at the behavior of a consumer and his attitudes towards risk, and we'll be calculating his risk premium under a few different probability distributions. So let's introduce him. For starters, his utility is the square root of W, where W is his wealth, or you could call it wage or whatever, it doesn't matter. Whatever his payoff is. We're going to start him out at 16 bucks. And you'll notice that there is a very not to scale graph over here where this portion, the curved part, is the utility function. You plug in a W and it's going to give you utility level. It's increasing at a decreasing rate. It's everything we've come to know and love about utility. And we have two events that can happen. Either this consumer will finish up today and have $9, in which case his utility will be the square root of 9, which is 3. Or this person will come out today with $16, in which case his utility, the square root of 16, is 4. Now there's two outcomes, and he doesn't know for sure which one he's going to get. And so that's where our risk is going to come in. Let's imagine a couple different ways this could go. There could either be a 10% chance that he'll lose and get $9, as well as a 90% chance that he'll win and get $16. Or maybe we could look at it if it was 50-50. Either event is just as likely as the other. Or maybe we can look at it if we flip the ratio altogether and we have it so that it's very likely, 90% likely, that he will lose and get $9, and only 10% likely that he'll keep his same wage. And so by comparing these different probability distributions, we're going to get some idea of how this person responds to risk. So the first thing I want to do is I want to calculate my expected wealth. Expected wealth. That's an easy enough place to start. Our expectation operators are weighted sums. You're going to add up the probabilities multiplied by their outcomes. So my expectation under this first distribution, my expected W, is 0.1 times, my wealth is 9 in that outcome, plus 0.9 times a wealth of 16. And this comes out to 15.3. Under my second probability distribution, there's a 50% chance of the $9 outcome and a 50% chance of the $16 outcome. And so on average, this thing comes out to 12.5. And for our last distribution, our third distribution, the expectation of wealth is 0.9 times 9 plus 0.1 times 16, which comes out to 9.7. And so what you're going to see as you move downward through these distributions, the more likely the bad event gets, the $9 event gets, the closer our average or our expectation gets to $9. And so this gives us 3 points along this line up here. We've got these possibilities, and there's infinitely more in between. We have these three outcomes that could happen. If we're 90% likely to land for W, our expected wealth would be 15.3. And then 12.5 at the 50-50, and 9.7 at the 90-10. Now, one thing you'll notice artistically, this graph is awful. It's very not to scale, but I don't care. I wanted to be able to compare these things. So this straight line that these colored dots are on is our expected utility of some probability mix of these two actual outcomes. And if the probability is closer to point A, we'll get points like this blue one, where A is more likely. If instead our probability is skewed so that we are more likely to end at B, we'll get points more like the green one. And so our point along this line gives us some idea of how likely each event is. And they give you your expected outcome. Okay, next, I want to calculate our actual utility at each of these levels. What if instead of playing this little gamble, you got to just take $15.3 and walk away? I'm going to say utility of expected wealth. So my utility function, and let's say I plug in E1 of W, my expected wealth under the first distribution. This is the square root of E1 of W, which is the square root of 15.3, which is 3.91. Let's see, similar calculation, U of E2 of W is the square root of 12.5, is 3.54. And last, the utility of E3 of W, the utility of my expected value under the last distribution, square root 9.7, is 3.11. All right, so what do these tell us? These tell us the utility that we would get if we were just given the average value of this gamble. And so what we want to compare it to is the expected utility. So for expected utility, we're going to go back to this kind of framework, where we're going to give a probability weight to our actual utility outcomes. There is under the green distribution, a 90% chance we get 3 utility, and a 10% chance we get a 4 utility. So let's formalize this a little bit. We're going to say, instead of the utility of the expected value, this is the expected utility. And this all makes sense in just a minute. At least I hope it will. So my expected, actually let's do it. Let's keep our colors going. Expected utility under the first distribution is 0.1 times my utility of the low event, which was 3, plus 0.9 times my utility of the high event, which is 4, and this thing comes out to 3.9. My expected utility under the second distribution is 0.5 times 3 plus 0.5 times 4, which is 3.5. And my expected utility under the third distribution is 0.9 times 3 plus 0.1 times 4, and that comes out to be 3.1. Okay, so a couple of comparisons. 3.91 is greater than 3.9. 3.54 greater than 3.5. And 3.11 is greater than 3.1. In all three cases, we would rather have certainty at the expected value than have just the risk of one or the other. And that's because of the shape of this curve. What we're comparing right now is the gap between my actual, from my expected utility and my actual utility. So this is my 3.91, and there's my 3.9. My utility at 15.3 is higher than my expected utility, if that makes sense. And if not, watch it again, find another video, read a book, come to my office, whatever. Likewise, my utility at 12.5 is 3.54, which is higher than my utility, my expected utility of 3.5. And my utility at 9.7 is higher than 3.11, higher than my expected utility, or my utility of the expected value at 3.1. So in all three cases, we are better off, we're happier not taking a gamble for getting the average payoff than taking the risk of maybe good, maybe bad. And that's what we call risk averse. And risk aversion will happen every time your utility function is shaped like that. Because it will always be that your utility function is higher than the expected value between 2 points. Okay, now that I've made that graph really ugly, let's do something else. Just like, let me get rid of some of these. Oh, geez. So, actually, I'm just going to double down, and maybe I'll draw a second graph in a minute. Okay, next. Well, if we're happier taking a certainty instead of a gamble, maybe, or not maybe, let's also be interested in knowing at what point are we just as happy with certainty as with a gamble. So if instead of comparing this thing vertically, comparing your expectation to reality or expectation to certainty at a certain point, what if we consider it horizontally? Some lower level of wealth would make us just as happy as a gamble with 9.7. Some lower level of wealth would make us just as happy as a gamble with a 12.5 average, and so on. So our next thing we're going to do, we're going to look at our certainty equivalent. Which this is just the level of wealth that will give us the same certain utility as the expected utility. So we've already got our expected utilities, so we're going to do, let's see, if I want to get my certainty equivalent for distribution 1, I'm going to be looking for some W such that the square root of W is equal to the expected utility of W. Or sorry, expected utility under that distribution. So what does this mean in English? Well, not really in English, but it means that I'm looking for some W where its square root is 3.9. So W squared equals, oh sorry, not W squared. So W is equal to 3.9 squared, which is 15.21, which is our certainty equivalent. So I would be just as happy having $15.21 exactly as I would be playing this first game where I have a 90% chance of getting 16 and a 10% chance of getting 9. So that certainty equivalent says, I'm willing to take less money to avoid a risk. And so with that, we can also get a risk premium. I guess I can do that now. So the risk premium is the expected value of W minus the certainty equivalent. So this is 15.3. That was our expected value, minus our certainty equivalent, 15.09 equals 0.21. So 15.21 is the level of wealth at which we're indifferent, which means we're willing to give up 21 cents to avoid the gamble. Oh, sorry, I did that math wrong, didn't I? Sorry, I recorded that incorrectly. Keep you guys awake. I wrote 15.21, which means there's a 0.09. I'm willing to give up 9 cents to avoid the gamble. Okay, let's do this for the other one. If I want to get my certainty equivalent, square root of W, it's going to be equal to the expected utility under red, 3.5, which means W is equal to 3.5 squared, which means W is equal to 12.25, which is our certainty equivalent under the second distribution. So if I want to get the risk premium, I take my expected value under distribution 2 and subtract the certainty equivalent. And I see that this person is willing to give up 25 cents to avoid the gamble under this distribution with the 50-50. Now the last one, it's the same idea. Square root of W is equal to, what was my expected value? 9.7. No, it is equal to my expected utility. Sorry, I got lost for a second. Is equal to 3.1. So 3.1 squared, which is 9.61, is my W, and that's my certainty equivalent under the third distribution, 9.61. So for his risk premium, I compare the expected utility, the expected wealth of 9.7, subtract the 9.61, and I get 0.09. So under the third distribution, I'm willing to give up 9 cents to avoid the gamble. So what are we seeing here? We're looking at these gaps. This gap is 9 cents. Doesn't sound like much. It's pretty arbitrary, though. I just made up the numbers. But it gives me an amount that I'm willing to give up to avoid the gamble. Notice, this gap is smaller than this gap. There is less uncertainty under green and blue than there is under red. Under green and blue with 90-10 distributions, you have a better sense of what's likely to happen. Whereas under red, you have very little idea. And so being risk averse, your risk premium will be highest under red and as you go towards the middle. Because out here and here, we have a better idea of what's going to happen. There's not as much risk for us to be averse to. Alright, I know this video was long, but hopefully it was useful. You figure out how to do expectations, to calculate utility of expected values, and compare that to expected utility. And we got our certainty equivalent and our risk premiums. For the record, if this person was ever going to buy insurance, he'd be willing to pay less than or equal to his risk premium to be fully covered. That's about all I got. I hope it was useful. If not, you wasted your time anyway. Don't waste any more. Thanks for watching.